Welcome. Today we're diving into the principle of mathematical induction, a powerful tool in mathematics. This principle allows us to prove statements about all natural numbers, even when direct verification seems impossible. Think of it as a domino effect. If you can knock over the first domino and ensure each one knocks over the next, all will fall. Induction is widely used in algebra, number theory, and computer science. Let's explore how this principle works, why it's so effective, and how you can apply it to solve complex problems. Ready to unlock the secrets of induction? Let's get started with the basics. Mathematical induction is a method of proof used to establish that a statement holds for all natural numbers. It's like climbing an infinite staircase. If you can step onto the first stair and you can always move from one stair to the next, you can reach any stair you want. Induction is especially useful for sequences, inequalities, and divisibility problems. The process involves two main steps, the base case and the inductive step. Let's break down each part and see how they work together to build a solid proof. First step in mathematical induction is the base case. Here we verify that the statement is true for the initial value, usually n equals 1. This step is crucial because it sets the foundation for the entire proof. If the base case fails, the whole argument collapses. Think of it as making sure the first domino is standing and ready to fall. Once the base case is confirmed, we can move on to the next step, confident that our starting point is solid. For the base case, we tackle the inductive step. Here we assume the statement is true for some arbitrary natural number k. This assumption is called the inductive hypothesis. Next, we show that if the statement holds for k, it must also hold for k plus 1. This step is like proving that if one domino falls, the next will too. By establishing this link, we ensure the statement holds for all subsequent numbers, completing the induction process. Both the base case and the inductive step are established. The principle of induction tells us the statement is true for all natural numbers. This logical chain is powerful because it allows us to prove infinitely many cases with just two steps. Induction is a cornerstone of mathematical reasoning, providing a systematic way to tackle problems that would otherwise be overwhelming. Let's see how this works in practice with a classic example. Classic use of induction is proving the formula for the sum of the first n positive integers, 1 plus 2 plus n equals n plus 1 slash 2. We start by checking the base case n equals 1. The sum is 1 and the formula gives 1 plus 1 slash 2 equals 1, so it works. Next, we assume the formula holds for n equals k and then show it holds for n equals k plus 1. This example demonstrates how induction can prove statements about sequences efficiently. Let's look at the base case for our sum formula. For n equals 1, the left side is just 1. The right side using the formula is 1 plus 1 slash 2, which also equals 1. Since both sides match, the base case holds. This simple check is the first building block of our proof, ensuring that our formula starts off on solid ground before we move to the next step. Now we assume the formula holds for n equals k. That means we believe 1 plus 2 plus k equals k plus 1 slash 2 is true. This assumption is our inductive hypothesis. It's a temporary belief that helps us build the next step. By working with this hypothesis, we can try to prove the formula for n equals k plus 1, extending the truth to the next number in the sequence. Complete the inductive step, we add k plus 1 to both sides of our hypothesis. The left side becomes 1 plus 2 plus k plus 1. The right side is k plus 1 slash 2 plus k plus 1. With some algebra, we can show this equals k plus 1, k plus 2 slash 2, matching the formula for n equals k plus 1. This confirms the formula holds for the next number, completing the induction. By confirming the base case and completing the inductive step, we've proven the sum formula for all natural numbers. This process shows the elegance and efficiency of mathematical induction. With just two steps, we've established a result that holds for infinitely many cases. Induction is a powerful ally in mathematics, making complex proofs manageable and systematic. You might wonder why induction is so reliable. The key lies in its logical structure. By proving the base case, we ensure the statement starts true. By proving the inductive step, we guarantee that truth carries forward from one number to the next. This chain reaction covers all natural numbers, making induction a rigorous and trustworthy method in mathematics. Mathematical induction isn't just for sums. It's used to prove properties of sequences, inequalities, divisibility, and even statements about algorithms in computer science. Whenever you need to show that a property holds for all natural numbers, induction is often the go-to method. Its versatility makes it a staple in many areas of mathematics and beyond. Number theory, induction is frequently used to prove divisibility statements and properties of numbers. For example, proving that a certain expression is always divisible by a given number for all natural numbers. Induction provides a systematic approach to tackle these problems, ensuring that the property holds for every case, no matter how large. Induction isn't limited to pure mathematics. In computer science, it's used to prove the correctness of algorithms, especially those involving recursion. By showing an algorithm works for the base case and that it continues to work as the input grows, we can be confident in its reliability. Induction bridges the gap between theory and practical application in computing. There's a variation called strong induction. Here, instead of assuming the statement is true for just one previous number, we assume it's true for all numbers up to k. This broader assumption can be helpful for more complex proofs, especially when the next case depends on several previous cases, not just the immediate one. Strong induction is particularly useful when each step in the proof depends on multiple previous cases. For example, in proving properties of sequences defined by recurrence relations, strong induction provides the necessary flexibility. It's a powerful extension of the basic principle, allowing us to tackle more intricate problems. Let's see strong induction in action with the Fibonacci sequence. Each term is the sum of the two preceding terms. To prove properties about Fibonacci numbers, we often need to assume the property holds for both n equals k and n equals k1. Strong induction lets us make this broader assumption, making the proof possible. While induction is powerful, it's not always the right tool. It only works for statements about natural numbers or well-ordered sets. If the base case or inductive step fails, the proof doesn't hold. It's important to carefully check each part of your argument to ensure induction applies and is correctly executed. A frequent mistake is assuming the inductive step is obvious or skipping the base case. Both are essential. Another pitfall is making errors in algebraic manipulation during the inductive step. Always write out each step clearly and check your logic to avoid these common errors. Visual aids can make induction easier to understand. Imagine a row of dominoes. If you knock over the first and each one knocks over the next, all will fall. This visualization helps reinforce the logic behind induction and makes the abstract concept more concrete. How does induction compare to direct proof? Direct proof works by showing the statement is true for all cases directly, while induction builds a chain from one case to the next. Induction is especially useful when direct proof is too complex or impossible. Knowing when to use each method is a valuable skill in mathematics. Induction is often used to prove inequalities involving natural numbers. For example, showing that 2n and 2 for all n greater than a certain value. The process is similar. Check the base case, assume the statement for n equals k, and prove it for n equals k plus 1. Induction provides a systematic way to handle these proofs. Induction isn't limited to numbers, it's also used in geometry. For example, proving properties about polygons such as the sum of interior angles. By showing the property holds for a triangle and then for an n-sided polygon, induction helps extend geometric truths to all cases. Combinatorics often relies on induction to prove formulas for counting arrangements or combinations. For example, the formula for the number of subsets of a set with n elements can be proven by induction. This approach simplifies complex counting problems and ensures accuracy. Recurrence relations define sequences where each term depends on previous ones. Induction is the perfect tool to prove properties about these sequences. By assuming the property holds for earlier terms, we can show it continues for the next, building the sequence step by step. In computer science, induction is used to analyze algorithms, especially recursive ones. By proving the algorithm works for the simplest input and then for larger inputs based on smaller ones, we can be confident in its correctness and efficiency. Induction bridges theory and practice in programming. The idea of induction dates back centuries with roots in ancient Greek mathematics. Over time, it became formalized as a rigorous proof technique. Today, it's a fundamental part of mathematical education and research, valued for its clarity and power. Induction remains a cornerstone of modern mathematics. It's used in research, teaching, and problem-solving across disciplines. Whether you're working on pure math, applied math, or computer science, induction is a tool you'll encounter again and again. While induction is a mathematical concept, its logic appears in everyday reasoning. For example, if you know a process works for the first step and continues to work for each following step, you can be confident it will work for any number of steps. This logical thinking is valuable beyond mathematics. Sometimes, induction is combined with proof by contradiction. If assuming the statement is false leads to a contradiction and induction shows it must be true for all cases, the proof is complete. This combination strengthens arguments and is used in advanced mathematics. Mathematical induction is a favorite tool in math competitions and Olympiads. Many challenging problems require creative use of induction, testing both understanding and ingenuity. Mastering induction can give you a significant edge in these contests. In higher mathematics, induction is used in abstract algebra, topology, and analysis. It helps prove properties of structures like groups, rings, and sequences. As you advance in your studies, you'll see induction applied in increasingly sophisticated ways. Infinite descent is a related technique, often used in number theory. Instead of building up from a base case, it shows that if a statement were false, it would lead to an infinite sequence of smaller and smaller counterexamples, which is impossible. This method complements induction in certain proofs. Set theory uses induction to prove properties about sets, especially those defined recursively. For example, proving statements about the size or structure of sets built step by step. Induction provides a logical framework for these arguments. In mathematical logic, induction is used to prove properties about logical statements and systems. It helps establish the validity of rules and theorems, ensuring that logical systems are consistent and reliable. Induction is a backbone of formal reasoning. Writing a clear induction proof involves stating the base case, the inductive hypothesis, and the inductive step explicitly. Each part should be justified and logically connected. Practicing this structure will improve your proofwriting skills and mathematical communication. To master induction, practice with a variety of problems. Start with simple sequences, then move to more complex statements. Always check both the base case and inductive step carefully. Over time, you'll develop intuition for when and how to use induction effectively. Induction often appears in exams both in high school and university. Being able to write a clear, logical induction proof can earn you valuable points. Remember to state each part explicitly and avoid skipping steps. Clarity and precision are key. Researchers use induction to prove new theorems and explore uncharted territory in mathematics. It's a tool for discovery, allowing mathematicians to extend known results and build new theories. Induction is as relevant in cutting-edge research as it is in the classroom. Induction exemplifies mathematical rigor. Each step must be justified and the logic must be airtight. This attention to detail is what makes mathematics reliable and trustworthy. Induction teaches us to build arguments carefully, one step at a time. Teachers use induction to help students understand mathematical reasoning. By guiding students through the base case and inductive step, they build confidence and logical thinking skills. Induction is a valuable teaching tool for developing mathematical maturity. Induction is a problem-solving powerhouse. When faced with a challenging statement about natural numbers, consider whether induction can help. By breaking the problem into manageable steps, induction makes even the toughest problems approachable. There's a certain beauty in induction. With just 2 steps, we can prove statements for infinitely many cases. This elegance is part of what makes mathematics so fascinating. Induction shows how simple ideas can lead to profound results. Let's recap. Mathematical induction is a proof technique for statements about natural numbers. It involves a base case and an inductive step. Induction is used in many areas of mathematics, from sequences to algorithms. Mastering induction opens the door to deeper mathematical understanding and problem solving. Congratulations, you've explored the principle of mathematical induction from its basics to its many applications. Whether you're a student, teacher, or math enthusiast, understanding induction will serve you well. Keep practicing, stay curious, and enjoy the journey of mathematical discovery. Induction is just one of many tools that make mathematics both challenging and rewarding.